Okay. Hi everyone. Can everyone hear me and see my screen?
Yes.
Okay, great. Um, so I'm going to get started. Uh, I'll try to monitor just the chat and answer your questions. Sorry if I don't answer your question, or you can also just unmute yourself. Either is fine. Okay. So today I'm going to start off by talking about base stacking. Then I'm going to talk about metal ions and nucleic acids, and then finally I'm going to talk about the sugar pucker and A and B form. So first, to start off with base stacking, what actually is base stacking? Well, it's the dominant a contributor to the stability of the nucleic acid double helix. And it's the result of intermolecular forces, or IMFs, between the planes of the base pairs. Okay. So in looking at the diagram on the left, this is just hydrogen bonding, which you are probably very familiar with. And then here, between the planes of the base pairs, we have base stacking interactions. So, base stacking. Okay. And then we should, think about base stacking, which IMFs are important to consider? Well, when we want to address that question, the first thing we should note are some special characters of the bases themselves. So the first character I want to talk about is that the bases are very flat and planar. And why is that important? Well, that means they have extensive surface area to interact with each other. So even though one van der Waals interaction might be weak, if you have a lot of van der Waals interactions, they make a significant contribution. Okay, and then the second thing I want to note is that the bases are aromatic rings. And not only are they aromatic rings, they're also heterocycles. And why do we care about that? Well, if they're aromatic rings, we know that they must be highly polarizable. And if they're heterocycles, we know that they will have net dipoles. Okay. Heterocycle. And so if we look on this diagram up here, here we can see this red region is a region of partial negative charge, and this blue region is a region of partial positive charge. And so here are the partial charges as a result of the bases being heterocycles and being aromatic rings. Okay, so why do we care about all these things? Well, these characters of the bases facilitate the following IMFs. And so the important IMFs here are van der Waals interactions, and electrostatic interactions. Okay, and so next, I want to talk about the influence of IMFs on the structure of the nucleic acids. So you hopefully today, I think, learned about different forms of DNA, A form, B form, and how they have different turns per base pair. And so this turn per base pair aligns the partial positive and the partial negative charges, the opposite partial charges of adjacent base pairs. And we know that, opposites attract, so this is a favorable interaction, a stabilizing interaction. Okay, and so another way to say that, looking at this diagram up here, is that the red, the partial negative regions, will align with the blue, the partial positive regions of adjacent base pairs. Okay, and finally, you also saw in class the example of a single-stranded RNA that adopted a helical structure even though it didn't have any base pairs. So that shows you that you don't need to have base pairs to have base stacking interactions. So single-stranded nucleic acids can adopt helical structures due to base stacking. Okay. So now that we've sort of brushed up on our knowledge of base stacking, I want to talk about the contributions to the stability of the double helix. Namely, I want to talk about the relative contributions from base stacking versus hydrogen bonding. And so, like I clearly already told you at the beginning, that base stacking is the bigger contributor here. And I want to talk about why that's the case. So in thinking about the stabilization offered by hydrogen bonding between base pairs in a duplex, we need to think about the net stabilization to really get a sense of whether hydrogen bonding can drive duplex stability. So what does that mean? That means we need to compare the energy of hydrogen bonds in a duplex, like you can see here in the figure on the left, and the energy of hydrogen bonds in a single-stranded nucleic acid on the right. Isabel, oh, sorry, Gian asked, can I scroll up? The filled out template will be posted afterwards, and Daniel just posted, yeah, the note template. So those will hopefully always be available before. Okay, so I said we need to compare the energy of hydrogen bonds in a duplex versus the energy of hydrogen bonds in a single-stranded nucleic acid. And so if we have hydrogen bonds in a duplex, right, so here I'm going to write energy of hydrogen bonds in a duplex, they're going to be between bases. So this is going to be a base-base hydrogen bond. And if you have hydrogen bonds in a single-stranded nucleic acid, they're going to be between a base and water, the surrounding water. And to find the difference between them, you just literally take the difference, subtract them. And so if the result of this is the net stabilization, the problem here is that although base-base hydrogen bonding interactions are pretty strong, these base water hydrogen bonding interactions are also pretty strong. So the difference, the net stabilization, is relatively small compared to base stacking. Okay. So now that we've talked about the relative contributions to duplex stability, I have a question for you. So like, feel free to answer it like verbally or in the chat. But it's, why is GC-rich DNA more stable than AT-rich DNA? And then as a hint, I put a figure so you can look at it. So I'm going to pause for about 30 seconds or until someone answers. Whichever comes first. Okay, so I see some answers in the chat, and mostly it's that GC makes 3 H bonds while AT makes 2 H bonds. So this is exactly why I asked this question. It's because this is a really common misconception. So let me show you the answer. So it's true that 3 hydrogen bonding interactions will be like a greater contributor to stability than 2 hydrogen bonding interactions in GC versus AT base pairs. But the hint that I put on the left, like they're pictures of the bases, and you can see they have this like arrow, and it's showing the dipole moment of the entire base. And it also has these like numbers with a D after it. So D is a debye, which is just a measure of a dipole moment. And basically all you need to like gain from this is that G and C have bigger dipole moments than A and T. And so in order to have a complete answer to this question, you can certainly mention that there's one more hydrogen bond in a GC base pair, but it's also really important to note, actually your main answer should be that GC bases have a greater dipole moment when compared with AT bases. So you're going to get increased electrostatic base stacking interactions if you have a stretch of GC base pairs. You actually don't even need to know that GC base pairs have greater dipole moments. Like if someone told you like, hey, GC rich DNA is more stable, tell me why. You know that, you now know that base stacking interactions are the bigger contributor to duplex stability when compared with hydrogen bonding. So you know that your answer has to primarily focus on increased base stacking interactions for stretches of GC base pairs. Okay, so hopefully that made sense. Now I'm going to talk about metal ions and nucleic acids. That's actually a really important thing to note. Yeah. Okay. So first I'm going to talk about magnesium because it's like it's just a very biologically relevant metal ion. So magnesium is an octahedral element, which means it can take on 6 ligands in the structure that I drew here. And that means it's often hexahydrated. It often has 6 waters. Okay. And these are just the different kind of metal ion nucleic acid interactions that you can have. So here is the metal cation, and here is the phosphate oxygen, so it's negatively charged. And so in the diffuse ion interaction, your metal is free to move. And the diffuse ion interaction is basically just a general charge screening effect. So it's a general screening of the negative charge from the phosphate by a sea of cations. And you can see that it's often mediated by H2O. Okay, sorry if my handwriting is bad. The uploaded notes will have better handwriting. And then you have outer sphere coordination, which is where the metal has ligands something. In this case, it's water in the diagram, and it's usually going to be water when we talk about it. And this ligand interacts with the negative charge from the phosphate. And then finally, you have inner sphere coordination, where the metal just directly ligands the negative charge from the phosphate. Okay, so why do we care about these metal ion nucleic acid interactions? It's because this is important in thinking about nucleic acid, the nucleic acid backbone, and other things, but you know. So I include a picture of nucleic acid here, and you can see that there are many negatively charged phosphates close together. So you have a lot of negative charges close together. And so, you know, metal ion interactions will be important to think about when you think about how to deal with these close together negative charges. Okay. And then finally, I'm going to move on to my last topic, which is sugar pucker and A and B form nucleic acid. So here, I'm going to highlight the ribose ring. And here, they're all depicted as coplanar, but in reality, moving one of the atoms of the ring outside of this plane that they're depicted as being on greatly decreases the steric clash, which decreases the energy. So it's favorable. Okay. And so here I've highlighted in red the atom of the ribose ring that isn't coplanar with the 4 other atoms. And I'm going to define for you what endo and exo are. And so endo means that this atom of the ribose ring that isn't coplanar is on the same side of the plane as the C5 prime atom. And then exo, as you might suspect, just means it's on the opposite side as C5 prime. Okay, and so we can just go through the diagram and see that here. So here the 2' carbon is facing the same direction as the C5 prime, that's endo. Here it's same direction, that's endo. Here it's in the opposite direction, that's exo. And here it's in the opposite direction, and that's exo. And so as you can probably already tell from the labels on the diagram, DNA can be A form or B form, whereas RNA can only be A form. So you guys can reply in the chat or verbally. Why can RNA only be A form? What is your thought?
Because it can't have the C2 prime endo as the DNA, so because it would cause steric hindrance of the OH on the C2 prime and the phosphate group of the C3 prime.
Yeah, and Lexi also responded in the chat. And so both of you guys are right. It's because of steric clash between the 2' OH, which is the difference between DNA and RNA. DNA does not have that 2' OH, and the 3' phosphate of the backbone. And so here, I included a picture of B form DNA. Sorry, I tried to make it very clear that this is B form DNA. And so you can see that in the picture, there's a 2' hydrogen, and the distance between the hydrogen and the 3' phosphate is only 1.9 angstroms. And so here, I'm gonna write that, 1.9 angstroms between 3' phosphate and 2' H. And so let's imagine if we try to stuff a oxygen in here, like if we had an OH. So we have the phosphate OH, we have the phosphate oxygen, and we have the hydroxyl or imaginary hydroxyl oxygen there. What's the van der Waals radius of oxygen? It's 1.5. And so if we had this scenario here, we can add the van der Waals radii of the 2 oxygens, and that'd be 3 angstroms, which is clearly greater than 1.9 angstroms. So, this is just like a very rough way for me to show you that clearly the 2' OH wouldn't fit. Okay. So that's all I have for right now. Does anyone have any questions? Or
I have a quick
if,
question, please.
yeah.
Do you mind scrolling back up to the like C2 prime Indo? And
Yeah.
I'm just, is there, I don't know how important this is, but like what's the difference between the C2 prime Indo and C3 prime exo?
Oh. First of all, the C3 prime exo, so I highlighted the atom that's not coplanar. So here the 3 prime carbon is not coplanar, and here the 2 prime carbon is not coplanar. And you can also probably see from the diagram that there's like a difference in the orientation of this substituent of the 2 prime carbon. Yeah, and I think it's like drawn better in your lecture notes. So
okay, but like will we need to like super accurately draw the angle of those bonds for those the C2 prime Indo, like the the hydrox, or yeah. Sorry, the either the hydroxyl or the hydrogen atom.
I never had to, but I'm not the teacher. I can't say for sure. But I think if you know that C2 prime endo means that the C2 is not coplanar and endo means it's in the same direction as C5 prime, I think hopefully that should be enough. But yeah, I can't say for certain, like you will never be tested on this.
Okay, thank you. I appreciate it. Yeah, thank you.
Anything else? Okay. And I would encourage you to like think about the question that I posed again, because that seemed to be like sort of, yeah, the answer was not obvious, and I think it's important to think about. Okay, so now Tyler will take over.
Okay. Can you guys see my screen? Okay, yes. Okay. So I'm going to talk a little bit more about the various forms of helices that you will see DNA and RNA adopt. First, I'm going to start talking about B-form DNA, which has, like, I like to remember 2 important numbers because it's kind of hard to remember all of the numbers. Basically, if you can recognize that there are 10 base pairs per turn and 3.4 angstroms rise, sorry, this should be per base pair, I will correct that. Per base pair, then you can just do the math to figure out that there's going to be 36 degrees rotation per base pair and a 34 angstrom rise per turn. Note that for B-form DNA to actually, DNA to actually adopt the B-form helix, it has to be able to adopt a 2' endo pucker. Do you have any questions regarding B-form DNA? Okay. So the next form of DNA, the next form of helix I'm going to talk about is the A-form helix, which has slightly different dimensions, and unfortunately, it's not these kind of just have to be memorized because it's a little bit the math is a little more general on this. So there's going to be 11 base pairs per turn and 34 degree rotation per base pair. I'm sorry, and 2.3 angstroms rise per base pair, which would be a total of 25 angstrom rise per turn. And the alpha helix is characterized by by both strands adopting a 3' endo pucker. Okay. Are there any questions regarding any of this? Okay, I shall continue. If I'm going too fast, please let me know. Feel free to interrupt me and...
Wait, I actually do have a question.
Okay.
Why is the rise per base pair different if it's still based on van der Waals interactions.
Let me just come in here because I think this is a little confusing, and it's because the bases are not perpendicular to the helix axis.
Okay.
So they are 3.4 angstroms because you can't overcome that van der Waals repulsion, but because it's distorted, it's you can actually see it in this diagram. The bases are not perpendicular to the vertical axis as they are in vDNA. So the rise per step is a little harder to relate to the actual distances between the atoms.
Okay.
But as Tyler said, the structure of A form is harder to describe simply because it's distorted away from the center.
So are there any more questions regarding A form helices? Okay, I shall continue then. So the third type of helix that was discussed in class is the Z form helix. And this one is unique because it actually adopts a left-hand helix instead of a right-handed helix like A form and B form. And generally, you'll see Z form helices in regions of DNA that contain many CG repeats. And, oh, I'm sorry. Okay, and something that is unique about the, another unique characteristic of the Z form helix is it's like with the A form and the B form helices, all of the base pairs will adopt an anti-conformation with respect to the sugar. However, the like when you have a Z form helix, the guanine will actually adopt a syn base orientation with respect to the sugar. And that is basically what's pictured in this, but this is adenosine because my picture does not have guanine. But do you guys?
Sorry, I have one kind of general question. So for A form, B form, and Z form of DNA, can these be found like within one chromosome, or is it like separate strands of DNA, or can they all be kind of intertwined within one like chromosome? Does that make sense?
Yeah, so basically depending on the conditions, like certain forms of DNA will be favored. However, you will sometimes see like Z form intertwined with B form, and like when that actually occurs, there will be a melting of the DNA strand at both ends of the Z form DNA. And there are various things that could actually cause this to happen, and we'll talk a little bit, I think Professor Kurian will talk about that a little bit in upcoming lectures when you start talking about like torsional strain.
Okay, what exactly is melting, or is that something that will come later?
Like it's actually when you have the change in direction of the helix, because the Z form helix is a left-handed helix, the base pairs in between the Z form helix and the B form helix will separate a little bit. They won't actually be properly hydrogen bonding with one another. So melting is generally a term that you'll use when you talk about like the actual separation of two strands of DNA, but it's just kind of a separation of the strands at the junction between those two helices.
Gotcha, thank you.
Okay, are there any more questions regarding the three forms of like helices? Okay, I shall continue. So I have one question. So if you were to form a hybrid of one strand of RNA and one strand of DNA, would you form an A form or B form helix, and why? Okay, so you all are saying A form, but why would that be the case? Okay, and yes, it is because RNA can only really adopt the A form helix because it can't adopt the C2 prime end of blocker. Okay, so I'm going to start talking about the major and minor groove within a single strand of DNA, like a double strand of DNA. Sorry, but the major groove and the minor groove are visually different. I'll actually show you on B form DNA. The major groove is, can you see my cursor? The major group,
Yes.
yes, okay. So the major groove is this large groove here. Like it's visually larger than the minor groove, and the minor groove is this smaller groove here. I will talk more about that here. So the major groove and the minor groove like present unique chemical signatures on their surface where they're like exposed to the actual groove. And the major groove actually presents a unique chemical signature for like all of the varieties of base pairs between like CG base pairs and GC base pairs, whereas the minor groove will only present unique chemical signatures between like the AT and the CG base pairing. Does that make sense to everybody? So if you look at the actual image, it'll show you. I personally, when I took the class, I didn't memorize this. I would just draw them out, but it might be helpful to memorize the order if that is something you personally choose. But you'll see that like there is a hydrogen bond acceptor here and hydrogen bond acceptor here, when hydrogen donor here and a hydrogen atom here. Whereas when you flip the base pairs, the actual order of this flips, and that's important because it allows for unique interactions between proteins that are interacting with the major groove, which I will talk about a little more. So the B form major groove is large enough to accommodate elements of proteins, like such as alpha helices, and can interact with the unique chemical signatures presented by the base pairs within. The minor groove is narrow, like more narrow and just generally less accessible than the major groove, but this doesn't necessarily exclude any molecules from interacting with it. So you will still see interactions with the minor groove occasionally, but generally speaking, the major groove offers more specificity. And then the A form helices have a major groove that's deeper and narrower than B form, and a shallower and wider minor groove. And generally, because the major groove is deeper and more narrow than the B form major groove, it's just generally less accessible to proteins that are trying to interact with the sides of the base pairs. Do you guys have any questions with those past two slides? Okay, I shall continue. Once again, if I'm going too fast, please tell me to slow down. I don't mind.
Wait, I have a question.
Okay.
Is there some kind of importance in having the minor groove be less accessible?
Not that I can necessarily think of off the top of my head, but I don't really know. I will look that up for you and see what I can provide, and I can post that on Piazza.
Yeah. So just to be clear, because the major groove is where proteins and alpha helices like interact basically. So some kind of importance in that specific section. I don't know. I was just kind of wondering that. But.
An example of something that you may think of that would interact with DNA would be like transcription factors, that you would want to have some sort of specificity for the promoter of a specific gene. And the major groove can kind of offer that specificity because it allows like you to differentiate between like, the unique sequences of DNA.
Okay.
Does that answer your question?
Yeah, that helps. Thank you.
So DNA is relatively easily deformed. Like there's a couple of examples of interactions with like, molecules that you'll see that will deform DNA to an extent. Like one is heterocyclic compounds that generally have nitrogen or oxygen present in the heterocycle, can bind by intercalation, which is the slipping of the molecule in between the base pairs of the DNA. So it slips between like two adjacent base pairs. And then like an example of a molecule that is interacting with the minor groove of DNA would be distomycin. And the distomycin can bind once to DNA, but can also bind twice to DNA with another molecule of distomycin adjacently, like adjacent to it. And when it does that, the minor groove has to expand to actually accommodate both of those molecules. And as such, it does like open a little bit to accommodate stuff like the molecules. And then one thing that you guys did discuss a little more in lecture would be the persistence length of DNA, which is basically the maximal number of base pairs where DNA can be considered rigid and is not easily bent. However, if you exceed this number, like you'll start to see DNA bend a little more, and you don't necessarily have to treat it as a rigid structure. So I do have one question relating to this, and it's basically that when DNA wraps around a histone, 150 base pairs will loop around a given histone twice. How can we explain this given that the persistence length is 150 base pairs? Do any of you guys have answers to this or any ideas?
Is it the electrostatic interaction that it makes with the histone? That the strong electrostatic interaction.
Yeah, so the actual histone has a series of positive charges surrounding it, and the negative charges of the phosphate groups interact favorably with those positively charged amino acids. And as such, the interactions are able to overcome the energetically unfavorable bending of DNA despite like below the persistence length. And that is actually all I have to show you guys today. Is there any questions that you would like me to answer? If not, we can move to the next presenter.
I had a quick question.
Yes.
In regards to this question, you guys said that 150 base pair loops wrap around twice in a histone. Is that meaning there's 250 base pair loops or one 100?
Sorry, one 150, so 150 base pairs will wrap around the histone twice. So it's like 75 base pairs per loop around the histone.
I see, thank you.
I'm sorry, I will work on making my wording more clear.
Oh no, it's totally fine. I just wanted to make sure I wasn't thinking that I was two 150 base pair loops.
So it is one 150 base pair loop.
Thank you.
And it loops around twice. Okay, that is all I have. I'm not sure who was presenting after me. I just actually can.
Yeah, Kevin, are you ready?
Can you guys hear me? Is the audio okay? I had to change my mic recently. Okay. So the first two slides that I had are just kind of like for background. I might have to go over them pretty quickly, but it was just to keep in mind that a lot of what comes into supercoiling, especially what happens with like the twist and the ride later on, keep in the back of your mind that it's because of base stacking. Now, like Rosa said, base stacking is what makes the DNA helix so favorable and why it wants to preserve that DNA helix, especially the 36 degrees of rotation between each base pair. You'll see that come back later. And Tyler just covered this, so I'm gonna have my notes posted in the actual handout later. I'm not gonna cover this right now. Okay, so supercoiling is a conformation that DNA takes on. And I think the easiest way to approach supercoiling is before you reach it, like in the cell, you just look at artificial supercoiling. So how can you induce supercoiling in a strand of DNA? So when you have your normal B-form DNA and it's fixed on one side, you can rotate the DNA either left-handed or right-handed to change the twist number. So if you were to add a twist to your DNA, that would be right-handed supercoiling. And if you subtracted a twist, that would be left-handed supercoiling. And I think this will make a lot more sense once I cover the rest of the terms and stuff. And again, the base stacking is what provides the restoring force. Sorry, you'll see this come back. So the twist, I think you covered this in more depth in class. I think Professor Kurian usually draws out a DNA helix to explain it. The twist is the number of times the DNA backbone goes around the local helix axis. And typically there are 10 base pairs per twist. So if you get something like 1,000 turns of bDNA, you will have, if the twist is 1,000, then you would actually have 10 times that many base pairs. So if you had 2,000 base pairs in your DNA, your twist would be 200. So whatever the base pairs are, if you take 10 base pairs, one twist per 10 base pairs. And that's how you convert base pairs to twist. Ride is another conformation of DNA, and that is the number of times the helix axis crosses itself. So if you had, in this picture, one end is fixed and the original twist is 1,000, if you rotate it left-handed, you reduce your twist by 1, but because of the base stacking, it wants to restore the twist back to 1,000 to be its most energetically favorable state. If the twist goes back up to 1,000, ride, which is originally 0, has to decrease by 1. So that's what supercoiling is. So this would be the ride. And this DNA is now considered supercoiled, negatively supercoiled. In addition to ride and twist, there's also linking number. And linking number is defined by the number of times the DNA strands cross each other globally. So in this picture, the twist is 3, the ride is 0, and the linking number is also 3. Typically, if you find relaxed DNA, the twist and the linking number are always equal to each other, and the ride will be 0. So you only really have ride when there's supercoiling. So how would you use this in, like, let's say, a question or something like that? If you went back to this example from earlier, the reason we could say that ride decreases by 1 from 0 is because of what it has to be to contribute to the linking number. So originally, before you did anything to the DNA, its linking number was 1,000. Once you rotated the DNA, you decrease the linking number by 1. But now, because it's fixed on both sides, L has to stay constant. So in this case, the linking number remains at 99. And the twist has to go back to 1,000 because of its base stacking interactions. And because of this, the ride is what changes. And this is the relationship between the twist, the ride, and the linking number. So as before, in the example, we increased our twist. No, the example before we decreased our twist. Sorry. Oh, okay, never mind. This slide is not really related to that. I prepared it a little differently. So if your twist increased, your linking number has to stay constant. So the only way that could happen is if your ride decreased. And this is actually what happens when you, or happens in the cell when there's DNA replication. When you make more, when you're replicating DNA, you're adding more twists to the DNA helix. And because of the way the DNA is held, one end is fixed by the polymerase. And because it's so long, it's technically considered fixed on both ends. The linking number has to stay constant. And the only way that's possible is if ride decreases. And when ride decreases, that leads to the negative supercoiling of the DNA. So I'll just write that out really quickly. So supercoiling is the consequence of DNA replication because you're adding more twists to DNA without changing the linking number. Because both ends are considered fixed. So the ride has to decrease to compensate, and that leads to negative supercoiling. There's also different forms of supercoiled DNA. So in this case, you're taking relaxed DNA, you're rotating it, and then you're fixing it together so that it's in a circle. It's still going to have the same interactions. The linking number has decreased, and now it has to stay constant. The twist has to go back to its normal, and in order to do that, the ride has to decrease by 1. And that leads to 2 equivalent forms of DNA, which are called the plectronemic and the solenoid form. And this next slide is kind of like a summary page of how each of these concepts fits together. So taking artificial supercoiling as an example, if you have a left-handed rotation, the result is going to be a negative ride because ride has to decrease, leading to negative supercoiling. And when that supercoiled DNA is converted to either a plectronemic form or a solenoid form, it'll take on these handedness. So the plectronemic will be right-handed and the solenoid will be left-handed. And the opposite is true for a right-handed twist into DNA. The ride increases, supercoiling is positive. The plectronemic form is a left-handed cross and the solenoid form is the right-handed cross. And yeah, that's all I have. Are there any questions? Oh, there was a question of why the plectronemic form is the opposite of the solenoid form. It just has to do with the way that they interconvert. So whenever a plectronemic form converts to a solenoid form, you're not doing anything to it other than just changing its form. You don't cut anything. You're not adding any additional twists. I think if you, I'm not sure if Professor Kurian is going to do this. He used to have like an example where he did this with a hose and he kind of like showed how they interconvert. It's just the way that it changes from one form to another. It has to be the opposite. Okay, thank you.
Shivani, you can take over whenever we're done with the concept session.
Okay. We can maybe take 1 minute of a breather and then get started.